Okay, welcome back. This is now 9.10, and finally we'll get kind of the official standardized method for producing these power series representations. So the method we saw in 9.9, I kind of think of that as a backdoor method, and I can kind of show you why. So this is section 1. What we'll be dealing with are the Taylor and Mclaurin series, the representations for functions. Okay, so very simply, let's try number. I don't know how simple this is going to be, but let's try number 4 from 9.9. Okay, so f of x is given as 1 all over 1 minus x, and then the center is 2. Is this a 1.9? This may even be this section. Okay, so it is kind of this section. All right. Before, I would have used a geometric. So I need to get this into the form 1 over 1 minus x minus 2 to get the center appropriately adjusted. So I'd have 1 minus 1 all. No, I think did I screw up 9.9 in that one problem when I turned it into summation form? So where the heck is the center? That was that 1. This guy. No, I'm good. Okay, I was a little bit worried that I didn't put the x minus 1 into the summation, but there it is. Okay, so in this character, I need to change the x into x minus 2, and then in doing so, what have you done? So if you distribute the negative, you get 1 minus x plus 2, so I need to go minus 2. And then this will be 1 all over negative 1 minus x minus 2, and then I still not nicely in the form of a over 1 minus r for the geometric. So I got to factor the negative into the numerator, but then that causes more problems, right? So now I have 1 plus x minus 2. So I'm going to have to go 1 minus negative x minus 2. And then finally I can say, all right, the a value is negative 1, the r value is negative x minus 2 to the n, and go from n equals 0 to infinity. Let me nice it up a little bit by kind of factoring that negative out of this portion. It'll end up giving me a negative 1 to the first times negative 1 to the n, which will be negative 1 to the n plus 1 times x minus 2 to the n. N equals 0. Okay, so there's the power series representation using 9.9 methods. 9.10, what we learn is that those Mclaurin polynomials and Taylor polynomials that we developed in 9.8, we can 9.7. We can use those and just kind of continue on infinitum, and you will produce the power series for the function. And there's really only one power series representation. You're not going to have multiple different ones. So the process that we give you, or that we've kind of already given you, should produce this series if applied. So let's go through that process. So if you remember what we did in the Mclaurin and Taylor sections, we took the derivative over and over, and then evaluated the derivative at the center. So in this case, the center is 2. And then we put the terms into the boxes for our polynomial. So you kind of want to do the same thing here. Let's rewrite it a bit so I can easily take derivatives. So taking the derivative here, power rule, but then you got a chain rule, so it'll be positive. So the power rule would give you a negative 1 in front, and then you have 1 minus x to the negative 2. But then the chain rule would give you another factor of negative 1. So you have 2 factors of negative 1 that would be positive. Okay? And for this, because I'm not looking for a finite polynomial, but rather a series, I kind of just enumerate until I see a pattern. Okay, so the next guy is going to be power rule, bring down a negative 2, but then the chain rule is going to make it positive. And it looks like I'm going to end up with kind of a factorial thing going on. 3 times 2 is the same as 3 times 2 times 1, which is basically 3 factorial. Bring down another 4, factor of 4, you get 4 factorial. I'll just do one more. And it's kind of clear what the pattern is, right? So you just go until you kind of see a pattern for the nth derivative formula. So the fifth is 5 factorial times 1 minus x to the negative 6. So the general form is n factorial times 1 minus x to the negative n plus 1. Okay. Of course, we want to evaluate these guys. So the first one would be negative 1. This is going to be positive 1, because it'll be 1 all over 1 minus 2, which is negative 1 squared. Negative 1 squared is positive, so it would be positive 1. So the only contributing factor of that 1 minus x to the negative 2, negative 3 is a positive or a negative 1. And it's alternating, so the second derivative is going to get you back to negative, and then you have that factor of 2. And then we have a 3 factorial. This will be negative 4 factorial. And then the general formula looks like it's negative 1 to some power, either n or n, it's always either n or n plus 1, and then times n factorial. So if the even terms are negative, we need to make this n plus 1. Okay, then finally, the formula, from before, when we were working with the polynomial version would have been like this, right? It would have been blank times whatever times 1 plus blank times, and our center is at 2, right? So x minus 2 all over 1 plus blank times x minus 2 squared all over 2 factorial plus blank times x minus 3 cubed all over 3 factorial plus etc. And then we would go all the way up to the nth version. So I have x minus, well, it should be 2, right? It's always 2, to the nth power all over n factorial. But now what we're saying is that we can just continue it infinitum, and we will get the power series representation for the particular function that we're working with. Okay, so now we're going to call that, we're just going to call it f of x, although we can't technically say it's really f of x, but we'll call it f of x in the notation. And it'll be the sum of the blank thingamajig, and we're going to go from n equals 0 to infinity of x minus c to the nth power all over n factorial, right? And so for our case, the thing that's going in the blank, it's negative 1 to the n plus 1 times n factorial. It's going to be this guy right here, right? So if we were just copy and paste, what do we get? We get negative 1, 1, negative 2, 3 factorial, all the way up to negative 1 to the n plus 1 times n factorial. Okay. So right here in this box, which I've made too small, I'm going to be putting negative 1 to the n plus 1 times n factorial, and plugging in, simplifying, the n factorials will cancel. I'll get negative 1 to the n plus 1 times x, the c value is 2 in our case. And we're going from n equals 0 to infinity. And looking back up, yeah, that's exactly what you get if you do it the backdoor method, right? Okay, so wow, that should be kind of mind-blowing. Hopefully it is. If not, well, that's math for you. But anyways, in general, then the expressions we'll be working with, the Mclaurin series is going to be this. The series representation for f of x is going to be the sum of the nth derivative evaluated at c divided by n factorial, which is basically what this thing right here was. Well, not quite, right? That part is just the nth derivative, and then I had the n factorial out to the side there. All right, so then times x minus c to the n. It's sort of written it. I always put the n factorial over, so it's the same thing then. But the thing that you're kind of figuring out is this part and this the nth derivative of c, and you're always going to have to do this process where you're doing the derivative and then evaluating the function. You're going to be doing a bit of a pattern identification, inputting into the template, so to speak, and then simplifying, hopefully. But there it is. So that's the Mclaurin, and then the Taylor is just the shifted version. So that representation, instead of 0, you have c. So this is just the Mclaurin version. So the c value is 0. Okay, so and then the Taylor, then you can put the c in there. But the idea is it's exactly what you did in 9.7. All right. If you master 9.7, this shouldn't be too big of a deal. It's just maybe you'll have a little issue with the summation notation, but hopefully that won't be too big of a hurdle for you. So let's take a look at number 2. We're just going to do a Mclaurin and then do a Taylor, and there are some other topics we have to discuss as well. Right, so now it's no longer polynomials, but rather series. And let's get the power series representation for e to the negative 3x, centered at 0. Right, so first off, you got to go through the derivatives and all that great stuff. So do you know how to take derivatives is what it comes down to. And again, you just do enough derivatives until you see the pattern. Usually I do about 4 derivatives, and that will do me. And then I'm going to evaluate them all at the center. And for my summation notation, what I really need is an nth term formula for the derivative evaluated at 0. Okay, so I'm hopefully going to identify the pattern and have this formula. And that's what's now going to go in my box. If you'd rather just write it out like the polynomial and then go plus ... that's fine too. It's just you're not going to be able to do that in your homework. Okay, so that's the only issue with it. The homework is going to want the summation notation. Okay, but on my test, if you can't remember the summation notation, just literally write out the first couple terms and then go plus ... and I'll be happy with that. Okay, okay, so let's get at it. Got to do a chain rule. Okay, so this will be 1, 3 squared, negative 3 cubed, 3 to the 4th. So what's the pattern? There's a negative involved. It's either going to be n or n plus 1. When I have 1, it's negative, so I just want to put n. So if it's 2, if I plug in n equals 2, I should get a positive out at this point right here. Because right, this is n equals 2, this is n equals 1, this is n equals 3. So when I plug in 2, I want to get positive 3 squared. So when I plug in 2, it'll be negative 1 to the n. N is 2, so it'll be negative 1 to the 2. That'll be positive 1, which is just what I want. And then there's some 3, a base of 3 raised to some power. Looks like when it's 3, it's 3. 4, its power is 4. So when it's an n, it's the power of n. Okay? And then I can just dump that into my box. And there I am. Okay. Like I said, if you just want to write out the first couple terms, like do the box kind of thing, like we did with a polynomial, put plus dot 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 to indicate it goes on forever, and then you can just put your numbers in here. All right. All right. Let's look at a Taylor version. So number 7 is quite annoying because you'll see the derivatives will snowball on you. And so what's going to happen is you're going to start looking for different methods to produce these Taylor series. Usually maybe a substitution, maybe work with an integral of an easier series, that kind of stuff. In this case, because the derivatives are so nasty, we're just going to find the first 3 non-zero terms. And I'm not even going to cheat. I'm going to, cheat a little bit. I'm not even going to pretend that I want to go through this. I have. I've done this derivative and this problem a lot, but I don't want to make a mistake. Well, let's see. Okay, so the derivative of tan is secant squared. And then here we have a power rule. So it's be 14 secant x. And then chain rule, the derivative of secant is secant tan. So this becomes secant squared tan. You see the issue? It's just going to get annoying and annoying. So now I'm thinking, all right, I got to do a product rule. So there's 2 parts here. First, I'll do the secant part. So you have to do a product rule, right? So first I do a power rule on the secant squared part. So it'd be 28. Secant x chain rule, so there's another factor of secant, another factor of tan. I'm leaving the other tan alone, so it'd just be 28 secant squared tan squared. And now take the derivative of tan, so that's going to give me 14 secant squared times secant squared, so secant to the 4th x. And already I'm quite annoyed, right? What I'm going to do at this point is just kind of copy down what I have in my notes. Am I on the 3rd derivative? In my notes, what the heck did I do in my notes? First, did I screw up my notes? Oh, I did. So this is the first, this is the second, this is the third. Now I'm actually on my 4th derivative. Huh, adding insult to injury, right? All right, so the 4th derivative turns out to be, when all is said and done, because you have to do a product rule on the first portion, and then you got to do a power rule with a chain rule on the second portion. So you should end up with like 1, 2, 3 terms. It's not that bad, I guess. The 2 terms will combine though, and you end up with 56 secant squared x tan cubed x plus 112 secant to the 4th x tan x. And then the 5th derivative is going to be, because you'll have to do 2 power rules on the 4th derivative to get to here. It's going to be 112 secant squared x tan to the 4th x plus 168th secant to the 4th x tan squared x, and then plus 448. And it's not a bad exercise to do it on your own to see if you can get this derivative. Tan squared x plus 112. I don't need the exercise. You do, though, right? That thing. All right. Okay, and that should do it. The problem, I only need 3 terms, but I did 5 terms. The problem is some of these terms are going to end up being 0. Okay, so anyways, f of 6 pi, 7 tan of 6 pi. Tan of 6 pi is 0, so that first term is 0. So that's why you have to do more than just 3. Secant is really cosine. Cosine of 6 pi is 1, so this will be 7. Whenever you see a factor of tan, you're going to end up getting a 0. So, regardless of what secant is, tan of 6 pi is 0. So the second derivative is 0. And the third derivative, that first term is going to be 0, and then the second term will just be 14. And the next derivative, that's all going to be 0, because they each have a factor of tan. And then the next one, the only factor that works will be the last term, so 112. Okay. So this one, they're not going to want the summation notation. They're just going to want you to, write it out in all of its glory. This is a Taylor, so be a bit careful that you write x minus 6 pi. I don't know why I'm making my boxes so big. Sometimes you do. Sometimes the numbers snowball on you when you got half these crazy blanks. Okay, so that should be enough. So what do we got? 0, 7, 0, 14, then 0 again, and then 1, 1, 2. And that should do it. You got to simplify it and then put it into your WebAssign. I wouldn't put one like this on the test. Just clearly, that would take too much time out of your day. Later on, it seems like they do that on purpose. Like you get to grad school and they'll put one question on your test that's like insane, and you have to have the kind of maturity to say, you know what, I'm just going to take a point on that one. I don't have time to do it. It's going to ruin all the other questions on the test. I'm just going to skip it. Okay. So yeah, I wouldn't put that one on the test anyways, because I don't believe in fool's errands and stuff like that. So anyways, next part is the binomial series. Sometimes use this in approximations or bounding this 1 plus x function, bounding it above, bounding it below. But anyways, we won't derive it. I'll just give it to you. You could derive it by going f of x and then f prime of x, f double prime of x, and then evaluating it at 0. But what you'll end up with is 1 plus kx plus k times k minus 1 x squared over 2 plus k times k minus 1 times k minus 2 x cubed all over 3 factorial plus dot 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 plus k times k minus 1 dot 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 times k minus n plus 1 x to the n all over n factorial. So you get this, it's like a quasi factorial thing in the numerator. It's just it doesn't go all the way down to 3 times 2 times 1. And yeah. Okay, so let's try one of these. Number 8, we have f of x equaling 1 all over 1 plus x to the 4th squared. So believe it or not, this is of the binomial form. I just have to rewrite it a bit, right? So this is really the same as 1 plus x to the 4th to the negative 2. So we need to replace x in our formula with x to the 4th, and then the k value is negative 2. Odds are, well, I think they want the summation notation for this one. Let's get the kind of the first couple terms and then see if we can get the summation formula. Right. Alrighty then, so here we go. So plugging in x to the 4th wherever I see an x, and then negative 2 wherever I see a k. So this would be negative 2 for k, and then x to the 4th for x, plus, and we have negative 2 times negative 2 minus 1 is negative 3, and then x to the 4th squared is x to the 8th over 2, plus negative 2 times negative 3 times negative 2 minus 2 is negative 4, times x to the 4th cubed is x to the 12th. You multiply the exponents. And then all the way up to negative 2 times negative 3 times negative 4, dot, 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 all the way up to negative 2 plus n minus n plus 1. Times x to the 4n all over n factorial. Okay. And let's see if we can kind of simplify it as we go through, because it looks like, there's a little bit of simplification here, right, on that. It looks like you're kind of always getting part of the factorial to cancel. It's one of these situations where you have an n factorial all over, and it's really n plus 1 factorial all over n factorial, right? The negative, how is that going to work? It looks like it's alternating. Like this term, the first term is positive 1, the second term is negative, and this one is going to be positive again, because you have a negative times a negative, and then this one is negative. So, okay, so let's get the formula going. It'll be the sum. There's a negative 1 that's alternating, and I'll start at 0, right? So when it's 0, I want it to be positive, so I'm going to put n. When it's 1, it's going to be an odd number. Negative to an odd number is negative, so it would be negative. Okay, that looks fine. Then I'm saying I could do a bit of simplification, right? So just investigating this guy a little bit more, what the heck is it? You have some negative 1 to the n, and then you have 2 times 3 times 4, blah, 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 all the way up to negative n minus 2 plus 1. So what is that? It's negative n minus 1, which is really a negative 1, which we kind of factored out into this negative 1 to the n, times n plus 1. It's n plus 1 factorial, folks. So that numerator is going to be negative 1 to the n times n plus 1 factorial times x to the 4n all over n factorial. So what the heck is that? That's going to be negative 1 to the n times n plus 1 times x to the 4n. So why is that? It's because n plus 1 factorial up here at the top on the right, n plus 1 factorial, of course, is n plus 1 times n factorial, right? So all that n factorial stuff's going to cancel, and you just have n plus 1 left over. And so that nth term formula for in your series is just going to be n plus 1. Of course, there's that negative thing you got to deal with, but we're saying that all the effect of the negatives is going to just alternate it. Negative, positive, negative, positive, negative. And then what you're getting is like 4 times 3 times 2, which is 4 factorial all over 3 factorial. The next one would have been, here, negative 2 times negative 3 times negative 4 times negative 5, which is 5 factorial all over 4 factorial. And then you would get x to the what's that next one? This is 0, 1, 2, 3, so 16. Of course, I ran out of room there. But yeah, so hopefully you see the pattern involved there, and that should be the answer they want. Okay, so what I did essentially was I kind of knew the form for the binomial, and then I was able to use the form as a template. Okay, this thing right here, and you'll see that in the book they give you basically a table of well-known Mclaurin series. Okay, so if we go to the book, in 9.10, it's all highly classified. I need to sign in 30 million times, like I'm working for the NSA here. No. Which section are we in? Chapter 9? Okay, 9.10 is where we need to go. So there's all these well-established series. So, I mean, if you played around series all day, you probably have them all memorized. Kind of like the integral of secant tan is equal to secant, that sort of thing. But where is it? 9.10. here it is. So, you know, you won't be able to do this on a test. You won't have this list, but in the homework you will. So in 9.10, I believe it even tells you, use the list to figure out the series for the given function. Yeah, so here it says table of power series, number 10. And what you can do is go to the list and then just do substitution like we were kind of doing here with the binomial series. Okay? And you'll find that that works quite well. All right. So, for instance, if I wanted to find the power series for this guy right here, this e to the, I have the list, in the list, the power series representation for just e to the x. The e to the x is the power series x to the n all over n factorial from n equals 0 to infinity. So how do I get e to the negative 3x? You're going to go f of negative 3x equals e to the negative 3x. That thing, all I'm going to do is replace x with negative 3x. And then if you want to clean it up a bit, you could, you know, pull that negative out. So negative 1 to the n times 3 to the n times x to the n all over n factorial from n equals 0 to infinity. And hopefully that will be the power series. Yeah, it's right there. So if you have these forms down and you have them memorized, it's usually you just do a substitution. Let's make that the quiz for today. So 9.10 quiz. Find the power series, or in our case, it's a Mclaurin series for, it's a representation for the function f of x equals e to the negative x, I don't know, squared. Okay, find the power series representation for e to the negative x squared. And all you got to do is take this form and do a substitution. Okay? Okay, so let me pause the video and I'll write it down in my notes what we got. Okay, so what am I doing here? I'm basically replacing x in that given series. Here is the given series. And you need to do a substitution to get your hands on f of x equals e to the negative x. So you're replacing x with negative x squared in that summation. Okay, okay, so hopefully that's easy. Right. So let's try that with number 11, I guess. So using the tables. Number 11 in the homework, we have f of x equaling the ln of 1 plus x cubed. I know from the table that ln of x is equal to x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed all over 3 minus x minus 1 to the 4th all over 4 plus blah, blah, blah. So to get ln of 1 plus x cubed, all I got to do is substitute in the, so I want to replace x with 1 plus x cubed. Right? Okay, so I'll have 1 plus x cubed minus 1 minus 1 plus x cubed minus 1 squared all over 2 plus 1 plus x cubed minus 1 cubed all over 3 minus blah, blah, blah. Simplify that. So that works out nice. You get x cubed minus x cubed squared is x to the 6th over 2 plus x to the 9th over 3. So I think the next one's going to be x to the 12th all over 4. And then summation notation it. So the formula, we'll start at n equals 1 to infinity. There's an alternating negative, so I got negative 1 to some power. I want n equals 1 to be positive, so I'm going to have to go n plus 1, right? So if I plug in 1, I'll get 1 plus 1 is 2. That will be an even number. Negative to an even is positive, so that first term will be positive. And then I have x to some power, and then divided by something. Okay. Something's easy. That's just n, because the first one is 1, the second one's 2, then 3. And then the exponent may be a little harder, but I think it's just 3n, right? So you plug in 1, you get 3. You plug in 2, you get 6. You plug in 3, you get 9. Yeah, so that will be it. Okay, great. Kind of more annoyingly, are doing kind of a workaround for dealing with products of functions that would result in these nasty derivatives where you have the product rule all over the place. Here we want to find, there's no real nice way to do it, but this is a shortcut in some ways. Okay, so I want the Mclaurin series for this product, and I want the first 4 non-zero terms. Okay, I know the Mclaurin series for e to the x. It's just 1 plus x squared over 2. You look it up. I know the Mclaurin for sine x. Sine is odd and cosine is even. So sine will always have the even, the odd exponents, and cosine will always have the even exponents. So look, sine of x is odd, so its expansion will look like this. Cosine is even, so it's going to have the parts that are missing. Okay, so as you get more familiar with it, you'll see all these kind of cool patterns emerging, and then there's ways I probably can incorporate complex variables in there somehow to get Euler's formula. But sine of x, if you wonder how the heck I remember, it's just from a lot of homework, and the fact that it's odd gives me the odd coefficient version, or the odd degree version. Okay, and then guess what? We're going to multiply these. Long multiplication, right? So it's basically just distribute. First I'll distribute the x, so I'm multiplying this times all of these. I'm distributing. Okay. All right, so what do you get? You get x plus x squared plus x cubed over 2 factorial plus x to the 4th over 3 factorial plus x to the 5th over 4 factorial. Then you go to the next term. Right? Now I need to distribute the negative x cubed over 3 factorial to all the terms. Okay, so, and then I'm going to line them up too by column on the bottom here. So negative x cubed over 2 factorial times 1 is negative x cubed all over, so it's 3 factorial. Then negative, it'll be x to the 4th over 3 factorial. And then negative x to the 5th all over 3 factorial. And then I'm going to distribute this next expression, the x to the 5th expression. So times 1. We'll put it way out here, x to the 5th all over 5 factorial. And x to the 5th over 2 factorial times 3 factorial right here. Sorry, I screwed that one up. In my notes, I got it. I didn't, that's why I did. I was kind of looking at my notes there. Is that right now? So the second row, this times this, this times this. Yeah, I lost the 2 factorial. And then the third one. Okay, I think that's all I'm really going to need, because all I need are 4 non-zero terms. And that probably some of them will be 0, but we can add more stuff in if we need to. So the first term is x, and then plus x squared. And then what we got? 1 over 2 minus 1 over 6. So this will be 3, 6, which is 1/2. So it's plus x cubed over 2, or x cubed over 3 apparently. Crap, 2 over 6 is 1 over 3. All right, there's the next term is 0 then. And so to get the fourth term, I need to go to that third column. And when all is said and done, it'll be negative 130 x to the fifth, and then so on and so forth. But there you get the 4 non-zero terms, and that will give you the first couple terms of your approximation. It's you know, it's still a lot of work, but if you don't maybe have the derivatives off the top of your head, this will work for you. You could also do long division. I think that you probably are good with this, though. For the homework, there's no long division there, but long division does come up in certain applications and combinatorics. I saw it. Anyways, let's move ahead to integration. Okay. So if you took stats, you probably had these huge tables when you dealt with the normal distribution. And what those tables did was basically what we're doing right now. They give you approximations of integrals that you just can't do by hand. Okay, you're not going to be able to do it with Chapter 8 methodology. So something similar to maybe a normal curve would be this integral here. It's not really similar, but it has the kind of same flavor. Usually the normal distribution curve will have like a e to the negative x squared over 2 factor in it. And then you'll be integrating this thing. And what they do in stats class is they have tables that evaluate these functions, or evaluate these integrals, and then you just look up the answer in the table. We have calculators now, obviously, but for some reason they're still forcing us to use the tables, become a teacher and do something about it, kind of thing. But here we are. So anyways, what I'm going to do first is a substitution, right? I know the power series for e to the x, just down here, by the way, is the sum of x to the n all over n factorial from n equals 0 to infinity. Please, on the test, do the methods I'm telling you, so derive the function. I don't want to put something that's super hard on the test, but if I put something that's too easy, then people just have it memorized. So I still want you to show work, okay? Don't be doing this stuff in your head. At least in the beginning. Once you get the MIT, then go nuts. Okay. So, anyways, what is this thing? It's the integral of the sum, and I'm replacing x with negative x to the ninth. So this will be negative x to the ninth raised to the nth power all over n factorial from n equals 0 to infinity. Let's make that look a little prettier. So I can factor out the negative 1, I get negative 1 to the n, and then x to the 9n, all over n factorial dx. You can expand it. Okay? We're going to need a summation notation probably eventually, but let's just go ahead and expand the thing, and then integrate term by term. So if I were to integrate the formula, it's going to be negative 1 to the n times x to the 9n plus 1 all over 9n plus 1 times n factorial. And I believe it will still have index of 0. Okay, but let's look at it expanded. So n equals 0 is going to give us 1, and then n equals 1 will be negative. X to the ninth all over 1 factorial, then plus x to the 18th all over 2 factorial minus x to the 27th all over 3 factorial plus blah, blah, blah. I need enough terms because they want you to approximate this thing with error less than 0.0001. Okay. The resulting series that you get is going to be an alternating series. And we can use the alternating series estimation theorem to get this, to get the appropriate number of terms for the approximation. Okay, so that's why I'm continuing out with these terms. Anyways, integrating the terms, you're going to get x minus x to the 10th all over 10 plus x to the 19th all over 19 times 2 factorial minus x to the 28th all over 28th times 3 factorial. Let's just do a couple extra terms. X to the 37ths all over 37 times 4 factorial minus x to the, I think it's 46 all over 46 times 5 factorial plus dot dot dot. We need to evaluate from 0 to 1. Let's make sure my index was correct on this summation on the top right here. Starting at n equals 0, yeah, that works. Okay. Plugging in the limits, then if I plug in 1, I'll get 1 minus 1 to the 10th is 1, so 1/10, plus 1 all over 19 times 2 factorial, minus 1 all over 28 times 3 factorial, plus 1 all over 37 times 4 factorial, minus 1 all over 46 times 5 factorial, plus blah, blah, blah. Minus all that evaluated at 0 is just 0. Okay, so I need not worry myself about the lower limit. Now I need to get that approximation such that the error is less than 0.001. Okay. So in order to pull that off, I'm going to take the summation formula here. And I note from the estimation theorem, s minus s sub n is always less than or equal to the next term in the series. Okay. Just the positive portion of it. So what is a sub n plus 1? Well, from this formula, a sub n plus 1 should be x to the 9n plus 10 all over 9n plus 10 times n plus 1 factorial, if you wish. Okay, so it's what? And we don't need the x part. That's just 1 to the 9n plus 1, which is just 1. It's the bottom part. Right, so it'd be 1 all over 9n, it's really 9 times n plus 1, which will be 9n plus 9, but then there's another plus 1, so it'd be 9n plus 10 times n plus 1 factorial. And what I'm saying is we need this to be less than the 0.0001. Okay. The dealio here is that you need not kind of work that out by trial and error, because the numbers are already given. It's all of these terms that you've just written out. Okay. So what you want to do is go through and check these terms. And the first term that's less than that 0.001, just add up everything that comes before it. Okay. All right, so that term you're looking at right there, if I were to put that in my calculator, I'm going to get 1 divided by 28 times 3 factorial, that's just 6, right? So that's 0.0059 something. That's not good enough. That's not less than the 0.001. Okay, notice this would be, with our formula, this would be an n value of 2. Okay. You want to be a little careful. N equals 2. This is n equals 0. This is n equals 1. This is n equals 2. So for the approximation, you would be doing the first 3 terms. Okay, go on to the next one. This is actually n equals 3. And putting that on my calculator, I got 0.001 something. Still not good enough. So n equals 4. I got 0.000181. Still not good enough. So I'm going to actually have to add on another term, which would have been a minus. Sorry. So that would be, no, it's plus. 1 all over the next guy, 54 plus 1 is 55 times 6 factorial. So we check that guy. I may have to do another one. I don't know. And if I put that in my calculator, that one's good. This one will be 0.123425. So we need those first terms, everything before that one we just checked, right? Because that was a sub n plus 1, basically. So for s sub n, you just take everything before the one that goes below the error. Okay, so that is what we want right there for our approximation. And it's really S sub 4. Even though there's 5 terms there, it's S sub 4. Anyways, if you were to then get the actual sum, this approximation, if you were to add up those things in that black box, you'd get 0.9213 for your answer. And that there is kind of the punchline of the whole chapter 9. Okay, so we're able to kind of convert functions into polynomials if you're unable to do the traditional methods that you learn in chapter 8 for integration. You can try to integrate that thing. You're not going to be able to pull it off with a U sub. It's going to fall apart. So you have to do this process where we are converting it using a series, and then we can just use a polynomial for the approximation. Okay? But there it is. As usual, thank you for watching, and I'll see you next time.